The first page of this worksheet asks us to only consider the E2 mechanism and the E2 products, and we should only be working E2 on this page. Now, for the first example here, we don't have an alkyl halide. What we have is OTS. Now, OTS stands for tosylate in organic chemistry. What we're given here is an ethoxide molecule. So remember, here's a sodium, and sodium is a metal. And 99% of the time when you see metal, it's delivering an anion in here. So we have this charged base here. It can also be a strong nucleophile. We'll also notice that the solvent is protic. See this proton here, it's protic. So that makes all of our charged strong nucleophiles that are also strong bases act more basic instead of nucleophilic. Now, it doesn't matter which beta hydrogen I'm looking at here. I'm going to take one of them away. They're all chemically equivalent. So with an E2 mechanism, I'm going to start my arrow here at the oxygen, and I'm going to come after one of these beta hydrogens. The electrons that were holding the carbon and the hydrogen together then fall down between the two carbons. And when that happens, because carbon will not expand its octet, the tosylate is then removed. So the product that is formed will look like this. Now, I do expect you to be able to name a compound like this. We have to find the longest carbon chain that contains the functional group. So I'm going to number from the top down, 1, 2, 3. So this is propene. And then on carbon 2, I have a methyl group. So this is 2-methylpropene. The next reaction, I also have this strong nucleophile and strong base. I have this sodium methoxide. But I know that sodium is just delivering the methoxide. The sodium's just hanging out in solution. Now, I am in a methanol solution, and that methanol is polar and protic. And because it's a polar protic solvent, that dampens the nucleophilicity. It increases the basicity, and now I need to analyze where my beta hydrogens are. So I have one beta hydrogen here, and I have a beta hydrogen here. And they can each be antiperiplanar. We don't have any stereochemistry here. So it is possible that these are both antiperiplanar. So when this reacts in an E2 mechanism, I'm going to show you the one at the top because that's going to be the easiest one for me to get to here. The base comes after the hydrogen, and the electrons fall down between the beta hydrogen's carbon, or the beta carbon, and then the alpha carbon. The alpha carbon is the one that contains the heteroatom. And then the heteroatom is removed, and that all happens in one step. So for that mechanism that I just showed, we could form this product. Now, if we go after this beta carbon or beta hydrogen, then I'm forming this is my product. This is going to be the major product. This is going to have a stability preference. And that's because the double bond is more substituted. And when I say more substituted, what I'm doing is I'm looking around the sp2 carbons here. And I've highlighted the sp2 carbons. I guess that's purple. I can't really tell. And there are 2 carbons on one side, and there's 1 carbon over here. So this is a tri-substituted double bond. On the other product, I'm looking at the sp2 carbons, and gosh, that's light. Let's see if this is brighter. The sp2 carbons here, and then I count how many carbons are bonded to those sp2 carbons. Well, I have 1 here, and I have one bonded here. So 1 + 1, this is a di-substituted double bond. And because it is di-substituted, it is less stable than a tri-substituted. Therefore, the compound on the left is going to be the major product, and the compound on the right is going to be the minor product. So how do we name this? Well, moving around a ring, if you have 1 double bond, it's defined that that double bond is between carbons 1 and 2. When there's a substituent, you also want to number so that the substituent decreases its numbering in relation to everything else. So because the double bond is defined as being between carbons 1 and 2, and we have a substituent on that sp2 carbon, then the carbon with the substituent and the double bond is going to be carbon 1. So this is a cyclopentene, and it is 1-methyl cyclopentene. And again, this was the major product. So this minor product, this is going to be called, let's see, this is going to be carbon 1 and 2 and 3. So this is going to be 3-methyl cyclopentene. And this is the minor product. For the next problem, we're also given a ethoxide being delivered by a sodium counter ion, and it's in ethanol. ET is the abbreviation for ethyl, and OH is alcohol. So we have ethyl alcohol or ethanol. The ethanol is a polar protic solvent. Therefore, it dampens the nucleophilicity and increases the basicity. So for this molecule, this 2-chlorobutane molecule, we need to find our beta hydrogens, and we have 2 beta hydrogens here. And I just drew them on opposite sides to differentiate them. So I'm going to come after this one first, and the base comes after the hydrogen that drops the electrons down to make a new pi bond between the alpha and beta. Oh, I didn't take my chlorine off. The alpha and beta carbons. Now the alpha carbon is the one that contains the chlorine in this case. So this is the alpha, and then this is the beta. So this is the compound that we make. This is called trans 2-butene. Now, what if we went after the other beta hydrogen? Well, if I go after that other beta hydrogen, and you'll have to work with me, I'm just looping around. The electrons still drop between the alpha and the beta. This is still alpha, and this time this is beta, which ejects the chlorine. But this time my product will look like this. Now this is going to be the minor product. This is 1-butene. There is no trans or cis associated with it because there are 2 hydrogens on this side. This is the major product. But we can also form one more product because we don't know this stereochemistry. We don't know if the hydrogen, this beta hydrogen is here or here. We just don't know. So it not only can we form the trans 2-butene, but we can form the cis 2-butene. Cis meaning that both of the carbon groups are on the same side of the double bond. For the next compound here, again with our ethoxide and ethanol, and it's warm, the 70 degrees Celsius, the warm, the hot, the delta, they all mean the same thing in organic chemistry. It's warm. Now we're going to go, we have to identify our beta hydrogens. So we have a beta hydrogen here, and we have a beta hydrogen here. We're going to remove each of those beta hydrogens in turn and make a new pi bond between the beta and alpha carbon. So we have, well, that's a little sloppy. We have this as one of our products. And if we remove one of the methyl groups, then we have this as our product. Let's name them. I need to find the longest carbon chain that contains the functional group, in this case, the double bond. So we have a pentene. And here, let's see, that's a 2-pentene. And we have 2, 3, 4 trimethyl 2-pentene. Now that's going to be the preferred product, and it's going to be the preferred product because the double bond is more substituted than this double bond. Now this is a 1-pentene. It is also tri-substituted a trimethyl, 2, 3, 4 trimethyl one pentene. But this one is di-substituted. It has 2 carbons substituted for hydrogens on either side of the double bond. So 2 carbons bonded to the sp2 carbon means this is di-substituted, whereas this one is tri-substituted. There are 2 carbons here. There are 2 methyl groups. So 1, 2, and here's a methyl group, 3. Ooh, I'm wrong. 4. It's tetra-substituted. There are 4 carbons attached. I was wrong. So this is still the preferred one because it is more substituted. And here for the next problem, we have a beta hydrogen here and a beta hydrogen here. Now this one is a little bit of a trick question because I don't think we cover it in my Organic 1 class, but I know we cover it later in Organic 2. But these particular reagents form what's called a Hoffman elimination product. A Hoffman elimination product doesn't follow Zaitsev's rule that says that we need to have the more substituted product. This one, because we have this big bulky base here, isn't going to go after this hydrogen. It's only going to go after the less substituted hydrogen, the less substituted beta hydrogen, the less substituted beta carbon. Wow, why was that hard to say? So this is the only product that we would form. 1, 2, 3, 4, 5. So this is a 1 pentene. 1, 2, 3, 4. So this is a 4-methyl. That isn't necessarily something that I would expect you to know in my Organic 1 course. However, if you are studying for the MCAT or something similar, you may need to know that. You'll have to consult your MCAT specialty books for that sort of thing. But that's what that's called. That's a Hoffman elimination. So for the next product here, or the next product we are predicting, we have 1, 2, 3 beta hydrogens, but these 2 beta hydrogen groups would be considered equivalent. So I'm only going to really look at this one, and then I'll look at this beta hydrogen as well. Now, again, we are removing the heteroatom. So this is my alpha, and here I'm going to do beta at the top. So I need to put a new pi bond between alpha and beta and don't lose the methyl group. I would number this here, 1, 2. So this would be 1 methyl cyclopentene, because in a ring, the double bond is defined as being between carbons 1 and 2. You don't need a 1 there. However, if you put a 1 there just to be consistent, I'm okay with that too. Now, the other beta hydrogen is on the methyl group, and that means we're going to form a new pi bond between the alpha and this beta carbon, which would look like that. So we would call this 1-methylene. That's what we would call this group, 1-methylene cyclopropane. Because this sp2 carbon has 2 carbons attached to it, and this one has none. This is a di-substituted pi bond. And this one, we have 1 carbon attached on this side and 2 on this side. This is a tri-substituted double bond, or yes, a tri-substituted pi bond. Therefore, this is going to be your major or preferred product. For the next reaction, this is going to be a Hoffman reaction. I probably should have taken these off, but for those of you who might need it, I'm leaving them in. We have a really bulky base. I mean, I think we can all see how big this base is. And when you have such a big, bulky base, you're only going to go after your less substituted beta hydrogens. So we would only form the 1-methylene cyclopropane with this. For the next problem, what we have is, now it's not a trick. Here we do have tosylate, and again, that's to emphasize a point for later on, but you only have 1 beta hydrogen here. Although this is a more substituted beta side, there are no beta hydrogens on this side. There are 4 bonds showing on that carbon, therefore there are no hydrogen atoms to remove. So the only product that can form is this product. And we would call this 1-phenyl ethene, or vinyl benzene. For this product prediction here, you have a lot of stereochemistry. You still have your ethoxide and your ethanol. So where is the reaction going to occur? Well, we have to find our beta hydrogen atoms, and you need to find one that's anti-periplanar. This hydrogen atom is going to be out on top of the ring. The bromine is on top of the ring, so this one is out of the running. So we need the hydrogen that's back here. That's the only one that's going to react. So we draw our ring structure first. The methyl group stays here. The ethyl group stays here, but now we have a new pi bond between the alpha and the beta hydrogen. So, or the alpha and the beta carbon. So let's see if we do this mechanism briefly. The base comes for the hydrogen. The electrons drop between alpha and beta. The bromine is removed. Nothing happens here with the methyl group. So let's name this compound. This is a cyclohexene. And I'm going to start numbering it here. 1, 2, 3. So this is 1 ethyl. 1 ethyl. 3 methyl cyclohexene. We do have some stereochemistry that we need to talk about right here. And this stereochemistry, let's see, the H is coming out towards me. So this side, I'm going to write this in a different color. This side would be CIP priority 1. This side would be CIP number 2, and this side would be CIP 3. We are rotating counterclockwise, but H is coming out towards me. So that means this is an R configuration. So this would be R, 1 ethyl, 3 methyl, cyclohexene.